I'm delighted that I can host this because both of these speakers actually have actually been very inspirational to me. Particularly for me, they stand for doing for applying proper statistics to applications and having in mind, and also basically promoting that you have to have a proper understanding for the application in order to do this. And this is something that I admire about the work of both of them. Also, this is going to be a very exciting paper, as I know, because I know this paper. Good. The meeting welcomes an online audience. Please keep microphones muted and cameras turned off unless called to speak during the open session later. A recording of the meeting will be posted on the RSS YouTube channel. If anyone prefers not to be filmed, let us know and we can edit that part out. If you experience technical problems online, use the support chat box and someone in our support team will help you. We actively encourage everyone to contribute to the discussion of the paper in the Q&A session later. Comments or questions can be posted in the chat. The paper will be presented by two of the three authors. It was published in the Journal of the Royal Statistical Society Series A. It was a discussion paper in 2007. And I'd now like to call on Mark and Adrian to present the paper, and Mark is going to start.
We'd like to thank the Royal Statistical Society for asking us to present this journal webinar. A lot has changed in the 17 years since Adrian and I read the paper to the society, and it is a good time to represent the paper and note subsequent advances. We want to recognise our co-author, Jeremy Tantrum, who's not present today. This paper is about the statistical modelling of social networks. In particular, we present a statistical model to capture various forms of clustering commonly present in social networks. We start with the social scientific theory, that is the motivation for the model, and then we'll cover the model itself. I will hand over to Adrian at that point to cover model inference and two canonical examples. One which is Samson's famous monk, and the other one which is the AdHealth network. But first, let's start with some important history. The models in this paper are a combination of latent social position ideas and model-based clustering ideas. It is important to recognize that the statistical model is motivated by ideas that have a long history in the social sciences. Perhaps the most important concept is the concept of social position. Position defines where actors are in their social system. An important concept is that of structural equivalence, defined by Lorraine and White as actors having identical ties to the same other actors. Feinberg and Wasserman extended this to mean identical probabilities of ties to those other actors. In addition, Katie Faust further considered the extension where the other actors need not be the same individuals, but just be of the same type. This idea of general equivalence led to the deterministic block models of Francois Lorraine, Harrison White, and others. Nowicki and Snyders placed this on a firmer statistical footing with their Bayesian analysis of the stochastic block model. By partitioning the actors into classes that are exactly generally equivalent, it is a simple, intuitive model for a complex social system. The work on structural equivalence led to the consideration of continuous social spaces originally implemented in a deterministic way using multidimensional scaling. It was also the theoretical motivation for the latent position model of Hoff et al. That we also consider here. We will fix ideas with some example networks. Frank Sampson in the late 1960s joined a cloister of monks and recorded their social interactions over a year. He asked each of the monks, of the 18 monks, which of the other monks they liked. The network here is an aggregation of that liking over a 12-month period. Nodes represent the monks and the ties the direction of liking. We see a general structural pattern of ties with mutuality of ties and a sense of a clustering or grouping. It is unclear how much this visual effect is an artifact of the unspecified graph layout algorithm. The second example comes from the National Longitudinal Study of Adolescent Health. In this study, 160 schools were surveyed, and the students were asked to nominate their friends within their school, up to 5 girls and 5 boys each. The figures of a small school of 69 students spread over grades 7 through 12. The nodes represent the students, and the number on the node represents the grade the student was in. Again, we see mutuality of ties and a higher propensity to have friends from your own grade. So a natural clustering based on grade is present. However, looking at grade 9, we see that there could be additional clustering beyond the actual grade as the grade 9s are split. Again, the question is the clustering based on grade sufficient to describe the social structure, or is an additional notion of clustering required? So let's look a little more into that. Clustering is often of interest, but it's very nuanced. So let's see if we can be more specific. A simple form of clustering is by the transitivity of relationships, whereby actors that have ties to a third actor are more likely to be tied than actors that do not. This can be thought of at the micro level as the clustering of ties within a triad. This transitivity can build on itself to lead to a broader cluster of actors that have high transitivity amongst themselves. A related idea is that of homophily on observed attributes of the actors. This is a tendency for actors to have similar attributes to be tied compared to actors that do not. If the 3 actors in a triad have similar attributes, this can itself induce transitivity and hence localized clustering. Many social networks exhibit clustering beyond what is explained by these, and it could be homophily on unobserved characteristics, whether they're exogenous or endogenous to the problem. And this can lead to self-organization into groups or so-called clusters at the meso level, even though the process is driven by ideas and processes at the micro level. So we see that clustering is a complex thing, and it has a number of different forms. This motivated us to come up with a statistical model that incorporates those forms of clustering and enables more formal inference about it. In particular, whether or not there is clustering into groups, if there is, how many groups there are, and how are the actors partitioned into those groups. Finally, and most importantly as statisticians, we want to express our degree of certainty about the entire process, in particular uncertainty about group memberships. So we'll start with the model here. The model is a combination of 2 components. First is the latent space model of Hoff et al., which represents a structural equivalence form. The second component introduced latent classes of actors via the finite mixture model of Frawley and Raftery. In this sense, the model represents elements of both structural equivalence and generalized equivalence. Let's briefly review these models. The Hoff model posits the existence of an underlying continuous social space. Within the social space, the actors have positions will represent by Zi, typically an RK. Let Xij be the dyadic or vector covariates on each dyad. And then we build a hierarchical model where the actors I and j are an unknown distance apart, specified through the z's, and then conditional on the distances, the tie variables themselves are independent. In particular, the model form is of the log odds of a tie between I and j, conditional on the positions and the variables, has 2 components, linear predictor type component based on the x's, and a distance function indicating a dissimilarity between the points. In the actual application here, we have the distance function is a Euclidean distance and represented in this way. So now I'll hand over to Adrian.
Okay, so now we move on to the clustering part of the model. And the basic idea is we've got a latent position model for networks where each individual has a latent position, unobserved latent position in the social space. And the basic idea of underlying the paper is that these latent positions are themselves clustering. So the clustering takes place at the level of the latent positions. And the basic idea is to model the latent positions as clustered into G groups or clusters, and this is implemented using the finite mixture model, as Mark mentioned. So this we have the Zi, which is the latent position in d-dimensional space of the ith actor. These are assumed to be independent and identically distributed according to a finite mixture model. And here we've got each component of the mixture is a multivariate normal, d-dimensional multivariate normal distribution with a mean mu g for the gth group, the mean of the gth group, and a covariance matrix, which is sigma squared g times the identity matrix. And here, basically, it's not necessarily required to have the identity matrix, but we chose that because of its simplicity and also because we found that when we allowed for more general covariance matrices, it didn't improve performance, and indeed it sometimes degraded it because it basically allowed allowed forms that weren't well supported by the data because it didn't impose enough structure. So we found that this was a good balance. So this captures common aspects of social networks, as Mark has just been outlining some of them. The position of actors, this canonical idea that social actors occupy latent positions in social space. Transitivity, which is that again, Mark mentioned, if I'm Mark's friend and he's Christian's friend, then I'm more likely to be Christian's friend. Homophily on attributes, that's the idea that, in a sense, birds of a feather flock together. So if people have similar interests, if they're, say, two people are interested in video games, then maybe they'll be more likely to have links than if they're not. Then individual propensities to form and receive ties, which is some people may be more likely than others. And in this model, this is not an explicit property, but an emergent property of the model, where this allows basically by the random part of this allows some individuals to have more or less propensity to form and receive ties. And then the clustering beyond those quantities, which are beyond those aspects that Mark has mentioned. And finally, it makes it very easy to specify more general networks with general edge values. So what we're looking at is binary edges where either there's a link or there's not a link. Quite often we've got intensities, like the monks either like one another or they don't, but we could ask how much do you like each of the other people, and that would be intensity. And also counts, if, for example, contacts between people are represented by the number of emails they send one another, then that would be a count that might represent the strength of the edge. And this is very easy with this model. So how can we do estimation and inference? Well, estimation, we developed in our 2007 paper, we developed two alternative methods. One was a two-stage maximum likelihood approach, which is relatively quick computationally and gave good results. And basically what that is, the two stages, the first stage is to estimate a latent position model without any clustering. And then the second stage is to cluster the estimated edges. But the second approach is a fully Bayesian approach using Markov chain Monte Carlo. And in that approach, both the latent positions and the cluster memberships are estimated simultaneously. And this, of course, as is often the case with MCMC, tends to be slower, more complex algorithmically, but to give better results. And it turns out that actually there are cases where estimating the latent positions and the clustering simultaneously improve the results quite a bit. So inference, the general inference proposed in our 2007 paper was a version of Bayesian model selection, where each number of groups is viewed as a separate model, and then we have the usual Bayesian approach of finding the posterior model probabilities, which are themselves proportional to the marginal likelihood or evidence for a model. And this is in turn approximated by a version of BIC. And this version of BIC basically added two components for the latent position and the clustering. And one aspect of this is if the preferred number of groups is 1, there's no evidence for clustering. So basically that provides inference about the question, is there clustering at all or not? So let's go back to the two examples that Mark introduced. The first one is Sampson's monks, where we're looking at inference about the presence of clustering and the number of groups. And here we have the BIC. On the x-axis, we've got the number of clusters. On the y-axis, the BIC, where higher is better in this formulation. And it's conventionally a difference of more than 10 is viewed as strong evidence. So here we see that basically there's strong evidence for clustering because the one group model down here has very little support from the data. And then 3 groups are strongly supported. And in a certain sense, this is the number of groups that were, quotes, known to be in the data. And that's because basically Sampson, well, there's a lot more information is available, not just the distillation of the binary edges that are in this particular data set. There were a lot of other questionnaires or other pieces of evidence. And also Sampson lived there for a long time. And so this was a real participant observer ethnographic study where basically he observed for a long time and did, in a sense, validate the quantitative conclusions. So there's a lot more evidence suggesting that there are 3 groups, and the inference based on this model using just this small part of the overall evidence strongly supports 3 groups. Let's look at the estimated positions, which we see here. The estimated positions in the latent social space are seen. So the x and y axis are just ordinates in the latent social space. And the White and Breiger, who Mark cited, they did a reanalysis of Sampson's data and basically said which monks were in which groups, and they identify them as Turks, young Turks, the loyal opposition, and outcasts. And so the young Turks were the red in the T, the loyal opposition L, and then the outcasts over here. And the group assignments from our methods are the same as those of White and Breiger, that used a lot more information. So, and then each of these is actually not just a dot, but a pie chart, a colored pie chart. And actually, there's very little uncertainty in this from this model, but we do see for this monk, there's a small probability they're identified as young Turks. This monk is identified as a young Turk, but there's a fairly small probability that he might also be an outcast. Let's go to the ad health data. And so again, this is a friendship network, as Mark mentioned. There were 69 school students in grades 7 to 12 from one school, so there were six grades, and each one was asked to nominate up to 5 boys and 5 girls as their friends. And the grade was not taken into account in the clustering. And here we have basically inference about the number of groups. Again, the number of groups or clusters is on the x-axis, the BIC is on the y-axis. And what we see here is strong support. Well, first there's clear evidence for clustering because there's little evidence for the one group model down here. And secondly, 6 groups are chosen by the BIC. Again, fairly decisively, although there's a possibility here that of 5 groups rather than 6. And this is fairly satisfying because we know there are 6 grades and then 6 groups. It seems like that's quite a plausible number. So it's the same number of groups as of grades. And here we have the estimated clusters. These are just the point estimates without uncertainty. We've got the 7th graders over here, the 8th graders, the 9th graders, the 10th graders, the 11th graders. Sorry, they're 10th graders here, 11th graders, and then we've got some 12th graders here. So so we see that there's a kind of in a sense, although it's 2 dimensions, but there's a kind of ordering that makes sense, and the students mostly line up with grades. The latent clusters are shown by color, and the grades are shown by number. And then there's good but not total agreement between grades and groups. Now let's look at the uncertainty about cluster memberships, which we have here. And here we see basically this, the 7th graders mostly are, there's not much uncertainty, although some of them, there's some possibility that they might belong to the group that is dominated by 8th graders. Here we have 8th graders, and all the 8th graders are mostly in the same group. And we've got a few that might be in the 7th grade group and a few up here that might be in the 9th grade group. There are actually 2 who are more predominantly in the 9th grade group. And here the 9th grade group, we see that actually they seem to divide, 9th graders seem to be divided into 2. And we have, but there's some uncertainty across these. And then when we move up to 10th grade, we see a very different story. We see that the 10th graders are over here, and then the 11th, and we see that there's a fair bit of uncertainty for some of them. They might be in the 11th grade group. And then the 11th and 12th graders are really no longer separated. And this, I think, overall tells a narrative of, when basically they enter the school, they're, the new students, they're kind of clinging together. And then the same in 7th grade and still in 8th grade. But then when we get to 9th grade, we start to see differentiation that's no longer purely on a grade basis, but probably interests and other characteristics start to really kick in. And then when we get up to 10th, 11th and 12th grades, we see that people are increasingly sorting and grouping probably according to partly other things than grades and age, but also their interests, whether they're jocks or nerds or musicians or whatever it might be. Okay, so some developments since, there's been quite a lot of developments since 2007. Our paper, which we're talking about today, has been cited over 1,000 times since then, and the methods have been used quite a bit. There's been quite a lot of work on extending the ideas that I'm sure the discussants will be talking about a bit. Some of these developments were summarized in chapter 10 of this book by Bouveon et al., published by Cambridge University Press in 2019, Model-Based Clustering and Classification for Data Science. So that, I think that's kind of worth taking a look at if you're interested in this. One of the developments was development by Krivitsky et al. 2009, adding explicit sender and receiver effects. I mentioned that the sender and receiver effects can be an emergent property of the model that I've just that we've described here, but actually explicitly adding sender and receiver effects can improve the model a lot, because we know in social networks there are the sender and receiver effects, you know, sociality can vary a lot between individuals. So putting that into the model improve things. Secondly, there's been the mixture of experts latent position cluster model, where basically you've got unobserved characteristics, or sorry, observed characteristics that can influence or partly determine group membership. And this developed by Gormley and Murphy, which Claire may talk about a bit, I don't know. And then some of the effort has focused on computation, because the we had this issue that clearly the Bayesian MCMC gives better results than purely maximum likelihood approach, although that itself is not bad, but it's very computationally demanding. So there have been various efforts to basically make the computation more efficient without sacrificing the performance. One of these is replacing MCMC by variational Bayes, and this was developed by Michael Salter-Townsend. And this was implemented using the beautifully named VB-LPCM R package, which is variational Bayes latent position cluster model. And then an alternative approach is to keep the MCMC computation, but speed up the likelihood evaluation step. And it turns out that basically the likelihood takes a long time to evaluate, because you're looking at all the n squared links, whereas in fact, or approximately order of n squared links, whereas in fact you don't really, the edges that don't that are not present, they're not very important to the inference. So the idea is to just take a small subsample of these instead of evaluating them all. And that greatly improves computational efficiency and effectively brings it from the order of n squared of the full MCMC or likelihood approach to order of n. So a vast improvement without sacrificing performance very much. The other approach has been developments of stochastic block models, which are the other approach to model-based clustering of social networks, the mixed membership stochastic blocks model, the stochastic topic block model, where the observations, if you like, the links are no longer just pure like binary links, but text, blocks of text, and this is a combination of the stochastic block model and the latent Dirichlet allocation model by Bouveron et al. 2018. And finally, recently in the last 5 years or so, there's been use of this and extensions to machine learning and artificial intelligence. I just mentioned a few of these here. The latent position cluster model for multi-layer network data by Souza and Betancourt. The K-deep variational autoencoders approach, which is effectively a latent space cluster model by Kakiolaru and Goldberger. I think there's a typo there. And finally, there's been interest in extending the latent space model to combining it with deep learning models. So the and Yang et al. Introduced the deep latent space model for graphs. So to summarize, model-based clustering of latent positions for social networks provides a formal model of social networks that incorporates clustering, and it permits inference. So a lot of so earlier social network analysis relied on kind of eyeballing representations, visual representations of networks, and this permits formal statistical inference principles, statistical inference about aspects of the social network, whether or not there's clustering present at all, if so, how many groups there are, who's in what group, and what's the uncertainty about the group memberships. And finally, the actors' latent social positions relative to one another. And it gave reasonable results for 2 examples. It's implemented in the latentnet R function due to Krivitsky and Handcock, and there have been extensive developments since 2007, including applications to quite a lot of other data sets. So that's it. Thank you very much.
Thank you very much, Adrian.
I should stop.
And
sharing.
Mark, for this. Yeah, I think when Claire starts sharing, you will automatically stop sharing. But you did it anyway.
Yeah.
Okay, can I ask now Claire Gormley for the first discussion?
Can you hear me okay, Christian?
Yes, absolutely. And also see your slides.
And did it just move?
Yes.
Perfect. Great. Thanks very much, Christian. Hello, everyone. It's a huge pleasure to be here this afternoon and to contribute to the journal webinar on the paper on model-based clustering for social networks. I think is clear from the talk itself, but especially those of us who've watched it over the last 16 or 17 years, the paper by Mark and Adrian and Jeremy Tantrum has had huge impact. I use the word significant thoughtfully here as statisticians in the audience, but it really has had significant impact. But the impact has been multifaceted. So it's been used in a large array of different applications, so like picked up and applied, for example, in ecology and finance and many others. I didn't go into a lengthy list here. But there's also been a key contribution from the software that Adrian just mentioned, for example, which I think is a really important part of our work. So it's great to see it's picked up and used in other application areas, but to facilitate that through the provision of really high quality software. And as of Friday afternoon, when I did a quick check, and there's almost 250,000 downloads of the software package, which is huge testament to the impact it has had. But then I suppose from a selfish point of view, from the statistical point of view, it's also had impact in statistics, in statistical research. And in particular, I think we can tag it as really having catalyzed significant advances, in particular the area of network analysis or statistical network analysis. My time is short today, so I'm going to pick up on two pieces of advances since the paper. One is, as Adrian mentioned, looking at the dependence on attributes of nodes when doing the clustering of social network data. And then if time permits, a few brief comments on the model choice aspect of the work, because there are lots of choices, numbers of clusters, dimensions, how attributes enter the model, and so on. But as I say, these are just two brief points, and again, testament to the work. It has opened and created many more interesting open research questions. So first, that point on how we can model or account for node attributes in the latent position cluster model, when our goal is to cluster. So picking up on the notation that Mark and Adrian introduced under the latent position cluster model, we model that probability of an edge as a function of that separation in latent space, so the distance between our Zi and Zj. But there's also the possibility to model that link probability as a function of relative covariates. So Xij, the relative typically difference between the attribute for node I and node J. And several of the discussion contributions, if you look back to the 2007 paper, probe this interplay between node attributes and clustering structure and queried the authors on it, and it was part of their subsequent response. So really, sort of the big question is that attributes may influence edge probabilities as they do in the original model, but they may also influence cluster membership, or possibly just influence cluster membership, or possibly just edge probabilities, or possibly not at all. And this, as Adrian briefly mentioned, gave rise to work with Brendan Murphy, who I think is on the call here also, where we took the latent position model and essentially embedded it in the now well-known mixture of experts framework, which was pre-existing. And this allows the attributes of the nodes to enter the latent position cluster model in different ways. But importantly, this yields different model interpretations, which I think is a key aspect of the work's contributions. So very broadly, a mixture of experts framework is very straightforward. It's just where we take those mixing proportions in this case, a finite mixture model, and we model them using a generalized linear model. So here I pull back a little bit and denote the the attribute data associated with node I as WI here. And in the original latent position cluster model, essentially what was called XIJ was just the difference between WI and WJ for nodes I and J, let's say. But under the mixture of experts model, we essentially model those mixing proportions. So here, the log odds of belonging to cluster G compared to, let's say, cluster 1 as a logistic, through a logistic function. And we model that as a linear function of the node attributes. So your log odds is simply a function of those attributes. And it gives us this mixture of experts latent position cluster model. So exactly the model that Mark and Adrian had on screen, with the slight change that now our mixing proportions are now node specific. Maybe a graphical model just to visualize it. This is the graphical model of the original latent position cluster model. Kind of on the right here is the clustering part of the model. Here are our node specific covariates in W, or attributes. We view those as X, when, let's say, the difference between those, and in the latent position cluster model, along with the regression coefficients, they feed into the observed links Y. But it's the clustering piece is sort of out on its own. In the mixture of experts model or framework, essentially, we essentially toggle between that arrow between W and X. And we allow an arrow, and again, can toggle that between the attributes W and the cluster. K here denotes the latent variable denoting cluster membership. So we allow attributes influence different parts of the model. So in our 2010 paper, we had a few examples, but one that I thought would be well known to many here are the now famous Lazega lawyers network data. So in the paper, we looked at the 71 lawyers in that network, and we looked at what's called the co-workers network, where each employee listed with whom they had worked. And in that data set, there's nicely a lot of attributes associated with each of the nodes. So seniority, gender, geographically where their office was, which at the time probably was more important or influential than it would be in today's world. Type, whether they practice litigation or corporate law, their law school and years, and with the firm and their age. So we fitted the 4 possible mixture of expert models where we toggle those where the covariates or the attributes can enter the model. And we compare them using the AICM, which was also arose around that same time, which in brief here is just a penalized version of the mean of the log likelihoods of a posterior sample. But we essentially use that to choose between our models. So this is the latent position cluster model. I won't go into it, but we have 2 clusters, 2 dimensions with no attribute data. This is just modeling our adjacency matrix Y. Each circle or triangle is a latent location of a lawyer. The grey lines are the links between them, and the colours are the resulting cluster membership, colour and shape. And the ellipses here are 50% posterior sets. We did inference through the Bayesian route, and we can obtain that. When we fit attributes only in the cluster membership, so we have the logistic model with attributes there, but no attributes in the link probabilities, our AICM suggests this is the preferable model. You'll note good consistency between latent locations between the 2 panels here. But interestingly, the cluster membership and the clustering structure in the network becomes much clearer. Then in contrast, if we fit the sort of the original latent position cluster model where we just put the attributes in the link probabilities, you'll see the latent locations change quite significantly, and also the cluster membership is difficult to interpret here. And on the right hand side is the model where we put covariates or the attributes into all parts of the model. And again, here you'll see good consistency when there are attributes in the link probabilities. There's consistency in the latent locations, and the cluster membership is much less clear. And our reasoning for this is that it's really important where you put the attributes in this model, because your latent locations have different meanings depending on where those attributes are. So the latent locations essentially account for any remaining network structure that you haven't accounted for by including attributes in the link probabilities intuitively. And essentially, if you don't have attributes in your link probabilities, your latent locations are explaining a lot more network structure or having to do a bit more work. If you're clustering, if that's really your purpose, is the clustering, your clustering structure appears to be much clearer when you include the attributes there. And again, that's due to the different role of these latent locations. But we get interpretability when you look at the regression parameters in that logistic regression on the cluster memberships. The type of practice is a very strongly informative variable in the cluster membership. So it's clear that litigation lawyers tend to work with litigation lawyers more often than with corporate lawyers, for example. And again, leveraging the excellent latentnet software, there is an R package that facilitates this. But it wouldn't exist if the latentnet software hadn't in the first place. And then very briefly to close, I just want to touch quickly on the aspects of model choice, because I think this has been a very rich area of development since the paper was presented. There's clearly alternative mixture structures that could be considered. There was a finite mixture considered here. So Adrian already mentioned, for example, there were grade of membership type models where you had partial membership permitted in the model, those sorts of extensions. There were extensions with infinite mixture models, and also with the possibility of sparse finite mixtures in a similar model. I suppose the leverage or the nice piece that you would get from using infinite or sparse finite mixtures is it essentially obviates that need for having to choose the number of clusters. You don't have to fit multiple models and choose between them. In a sense, that becomes naturally part of your inference. And importantly, if you're doing this in a Bayesian framework, it allows you do posterior inference on G, so we can actually quantify our uncertainty on that number of clusters. And then finally, a key part is, what is the latent dimension, which here I've called the E. And largely, if you pick up most of the applications of this model, we choose 2 because we can put it on a slide and it looks good. But there has been some work using non-parametric shrinkage priors to infer the number of dimensions in both the projection model and the distance model version of the latent position cluster model. I just pick one example here. It's work again with Michael Fopp, who I believe is on the call, where we looked at a nervous system binary network from worms. And on the left is the BIC that you get from the latent position model. This is not in a clustering context. And you can see it's difficult for us to choose between whether there's a 3 or 4 dimensional latent space here. But we proposed a model that puts a shrinkage prior on the variance of the latent position, so it shrinks as the dimension increases, and it allows us to do posterior inference on the number of dimensions. So you can see agreement here. It's saying there is confusion between 3 and 4, but we can quantify that possibility. And indeed, we have a currently under revision paper where we put those 2 pieces together and use a non-parametric prior on the number of clusters and the dimensions, and you obviate the need for at least some model selection in that regard. I don't have time to talk about model choice for attributes, but that's another, again, piece of work to be done, but there has been some done by, again, some of the people on the call. Model fit, I think, is probably our biggest outstanding piece that as a statistical community we need to tackle. There has been some work done in this, but from a network modeling point of view, but I think there's much to be done in thinking about model fit from a clustering point of view. How do we model it, validate assumptions of the model? And importantly, picking up on Adrian's last point, positioning this model in that broader family of latent variable models. And you can see it really is beginning to link into things like latent factor models, which are now variational autoencoders, and seeing the linkages between this work and really emerging areas. Here I could have talked for longer, but I would like to thank Mark and Adrian and Jeremy for really stimulating an excellent area of statistics.
Yeah, thank you, Claire, for an also stimulating discussion. And now I'd like to call on Niall Friel.
Folks, it's a real pleasure to present to you today. So Mark and Adrian both have been leaders in the area of statistical network analysis for years, and the work has been very influential widely in the field, but personally from the work I've tried to do myself over the years. So real pleasure to be here. So the paper has been hugely influential, and I think in terms of the application areas that have arisen as a result of their work, and also the latent position work of Hoff et al. 2002. So here's just a few examples from conflict networks, trade networks, neuroscience, protein sequence data, epidemiology, and so on and so forth. So it's really had an incredible influence. And it was interesting to read the discussions of the paper while preparing this, and a topic that arose from a few discussions, particularly Bisag and Andrew Gelman, was the idea that networks, they'll they're a snapshot in time, so there's obviously interest to model how they progress and evolve over time. And I want to spend just a few minutes talking about some work that's been done in that area. So again, dynamic networks, it refers to how the network has evolved over time, typically with similar sets of nodes over time. The latent space approach, so it's been extended to this context. The application that I want to talk about, and it'll explain, I think, some of the ideas of the latent space approach, is one involving this concept of interlocking directorates. This is the idea where a director simultaneously sits on two companies at the same time. And there was a lot of actual media interest in Ireland at the time around the time of the Celtic Tiger crash to see, was interlocking directorates a sort of facet to explain the crash. So our data here is of the form of a bipartite network. Bipartite because it involves two node sets, the companies and the directors. So a director is linked to a company if that director sits on that company's board. Companies don't link to companies, nor directors link to directors. So it's bipartite. And it's a network that evolves over time. So rather than a two-dimensional adjacency matrix, it's now three-dimensional. So Yijt is one if director I is a member of board J at time t. And this network evolves over time and zero otherwise. We model it with a latent space approach. So the red nodes denote companies, blue denote directors, and a link happens if a director sits on that company's board. The idea is to see across time how this network evolves. And the intuition with any latent space model, in this case, is that in particular that positions of companies and directors in this two-dimensional space are such that directors which share multiple boards should be close in the latent space. So here's just a kind of brief picture of how the likelihood model looks in this case. So again, it's a logit type of model. And, excuse me, we introduce two types of latent positions, one for the directors, X, and W's to denote the companies. And the edges and non-edges evolve over time, but the evolution of edges depends on what we call an edge persistence parameter, and non-edges occur with non-edge persistent parameter beta. And as usual, the important element of this is the relative distance in the latent space between directors and companies captured by the last term in that logit equation. And apology, we model the data in a Bayesian way. And one of the, I think, interesting and useful features of the latent space approach is that it allows us to see how the actors evolve over time in this instance. So really what we're kind of seeing here is that companies tend to move closer towards the middle as the study progresses up until around 2007, 2008, when the crash happened. And actually, the picture you've seen here is the posterior mean positions of the companies and actors over time. And actually, we can do a kind of quantitative analysis of just how closely linked the companies were by examining the empirical posterior variance of the latent company positions over time. And what we see pretty much is that the company positions tend to get closer and closer in the latent space up until when the crash happened, and then more or less stabilized at that level of, let's call it, interlockingness. So it gave us some evidence that interlockingness was a feature of the company director evolution over time. But of course, there are many more papers in this area, and I want to point to three that I think were particularly influential. Sarkar and Moore had a paper in NIPS in 2005, and it obviously predates the latent cluster paper. So it's based on the Hoff et al. Paper 2002, a very influential paper, which was extended by Sewell and Chen and JASA in 2016. Sewell and Chen's idea was to allow each actor to have a trajectory over time in the latent space. And Durante and Dunson, around the same time in the Annals of Applied Statistics, extended that to allow for a continuous evolution of the latent trajectories via a Gaussian process. So a lot of work in this area over time. Just to point out some, I think, pretty much open questions really around computational scalability, and Adrian has touched on those a little. The problem is that for the latent space approach, you need to calculate the distance between all pairs of nodes, and there's n choose 2 of those, so it's quadratic in the number of nodes, so it becomes a problem very quickly. And when you have a temporal network, then the problem is exacerbated. So what has been done? So variational approaches. So Mike Salter-Townsend and Brendan Murphy have put together a Bayes, variational Bayes approach. I think Adrian touched briefly on the case control, like likelihood approximation. The idea here is that one could possibly sample the non-edges, which are more abundant than the edges, which have a kind of case and control analogy, respectively. Together with Riccardo Rastelli and Florian Mir, we did something similar by trying to come up with a grid approximation of the latent space, very similar to the case control idea. But the point is that all of the methods just described, they're all approximate methods, and they have a drawback from that point of view, but also they only apply to networks up to 1,000 nodes or so. So networks are observed often with much larger size. So what do we do? So I think it's an opportunity for future work, and it will be interesting to see how work in this area evolves into the future. So finally, again, just to thank Adrian and Mark and Jeremy Tantrum. Thank you so much, everybody.
Okay, thanks a lot. Thank you to all presenters today for their excellent and insightful talks. Now we'll move on to the open discussion Q&A session. We'd like to encourage the authors to apply, the speakers to respond to each other, and for audience members to comment or raise a question on the paper. The fact that we are quite late actually prompts me to say probably we should really give precedence to people from the audience who have questions. So is there anything? Maybe the best thing is to raise your hand if you want to ask something or say something. My idea was actually not to give me the precedence, but actually, there's John Hind has a question.
Hello. Okay. Thanks very much for the very interesting presentation and talk. I've just got a very simple question, and it's really relating to this, that any trade-off there is between the dimension of the social space and the number of groups that there may be in any setting. And particularly, does that get much more complicated with the examples Niall was talking about when you're allowing things to evolve over time? Does the evolution happen in dimension or in group structure? Or, well, any comments? Much appreciated.
I'm happy to have a quick shot at that. I mean, as the dimension goes up, it just, as we know very well from the curse or the promise of dimensionality, you get an enormous amount of locations to put these additional groups. So the dimension of the space is very important because it does enable large numbers of groups that can stay away from each other and hence represent more complex forms. But I just have a hesitation to do that just because of the flexibility of those dimensions.
We have Andre Sraka. Where's the second question or comment, please?
Thank you. Thank you for nice presentation. Two short questions. Firstly, in recent years, I think there has been a lot of discussion about network archaeology, which is a method for dynamic networks that you mentioned, and it includes clustering. There has been a discussion paper by Crane and Chu. Could your approach also be applied to this method? It is basically based on how to derive the root vertex in a dynamic network, including clusters based on growth processes like preferential attachment and similar. And very shortly, second question, you mentioned the specifics for large networks, not for high dimensional that we just heard. Is anything specific that you would recommend to extend it to very large networks, which are very present in these years? Thanks. Thank you.
Well, I'll have a brief shot at the second one. It's a little bit of a side note, second part of the question. When we deal with very complex networks, I think or very large networks, I think it's very important to step back and ask ourselves about the processes that generated them and whether a relatively simple or even from our perspective, a complex model is going to capture that enormous complexity. We know the number of relationships goes up like the square of the number of nodes. So I would just ask the question, should we be fitting any form of these class of models to very large networks, 10,000 nodes? I think what we'd really need is some additional theoretical, that is substantive motivation to break down the structure and then fit separate models to the subcomponents of that structure. I believe that better is a much more important approach than sort of hacking away, so to speak, and trying to extend these models out. The networks are complex, and the larger they are, the more complex structure is represented in them.
Thanks.
Okay. Now we have F. Panero. I can't see your first name, but anyway.
Yeah, it's Francesca Panero, Sapienza University. So thank you very much. So I have a very down-to-earth question regarding MCMC. So do you all code this, like also to discuss sense as well? Do you all use R, and do you all like hard code this, or like have you ever used like probabilistic programming languages? Do you have you have any insights about what you prefer? Because like I'm trying to move, like not to spend all my time computing derivatives to perform HMC when I do networks, but then I try switching to NumPyro, for example. So talking about Python here, but as soon as you step out of, I don't know, like probably like normal distributions, and if you want to work more like on likelihood tricks to like maybe lower down the computational complexity, then I'm not really able to do that. So I don't know if anybody has found anything there. Please share. Thank you.
I have a meta comment to make. I think it's really important that we as statisticians publish open source, really usable code. And the reason is it addresses a lot of your concerns. If one person codes at the very low level to get the efficiency, that can be used as a building block for others, either directly modifying that code or just building directly on it. And so we as a discipline can gain from the work of others. So to some degree, I think the solution to this is to try to work collaboratively, or at least cumulatively in terms of the work, so we don't have to repeat the very hard work of coding at a low level for efficiency. Yeah.
Yeah, I'd just add that I think that there's been a lot of concern and discussion in recent years about transparency and reproducibility and all these things. And I think that, there's a supplementary information about details of methods goes some of the way towards that. But actually, providing code, the actual code that was used, it's kind of the ultimate supplementary information, because it gives the precise information about exactly what was done. And so it has that purpose of really, making transparent in a very a complete way what was actually done, which no paper can really do. So I think, and I think in terms of these things of also making the whole enterprise more efficient by, so that people don't have to reinvent the wheel is another aspect.
Just a little anecdote on that. The paper describes what you thought you were doing. The code describes what you actually did.
Niall, you want to add something?
Yeah, I just add that so probabilistic programming, so Stan and so on. So I think they're probably out of reach for the latent space approaches because of the discrete kind of question of what nodes are allocated to what groups, and Stan doesn't like discrete parameters. All I'd say is that it can be challenging, particularly the applications over time, or is sometimes quite slow. And I think in practice we've used C, but 100% repeat what Mark and Adrian have said. Reproducibility is absolutely essential. Without it, I'd almost say papers shouldn't be published. But there you go.
Sorry, maybe I can just close off on that by saying the ME+net package that I mentioned very much uses the work that was done by Mark and Adrian and co-authors. It uses their R package to get starting values. So our MCMC actually only runs very briefly. So it leverages the work that they did. So thank you. And adds a little bit on, but it is practically in R and leveraging the generosity of others.
Do we have further questions or comments? I can add one. So when Adrian presented his part, I basically thought, okay, there were these two approaches, right? One approach is you estimate the latent space and then you cluster on it, and the other approach is you basically do that together. Now, you should expect that if you do it together and the model is true, you will have better results, right? Because all the information is basically used in all the steps. But actually, of course, in reality, there's no such thing as a latent space, right? It's kind of a construct in order to visualize something. And then I wondered whether running the model in an integrated way will actually have the effect, because when estimating the latent space, also the cluster information is used, that the observations in the clusters are put more together, so that the clustering is basically more pronounced than if you estimate the latent space without the clustering. So the question is, A, is that so? And B, if it is that actually a good thing? Because you may think that kind of the fact that you are assuming clusters makes the result more clustered.
Well, maybe I can have a stab at that. I think you're absolutely right that that's what the Bayesian approach does. So if you're saying the three group situation with the monks, it does tend to, because it's a model where the cluster positions have a sort of a prior that involves the three groups, and there's a certain amount of shrinkage, but it's kind of local shrinkage within each group of exactly the kind that you describe. I think that is the kind of danger that, so you're saying there's a danger that you'll artificially induce clusters that aren't really there. And I think that's really alleviated by the model comparison aspect, so that if you've got, say you've got two clusters in reality, and then you fit a three cluster model and you find three clusters because you're kind of shrinking, you're doing what you're mentioning, Christian, but actually the overall thing will say, well, actually there are two, so it'll be less likely to find that there are three. So I think that that helps things, and I think one of the reasons that we found that the performance with the two group, or sorry, with the integrated approach, is that essentially you've got, when you're looking at clusters, often the clusters are fairly small, so the amount of data is fairly small, and the clustering structure functions in the hierarchical model as a kind of a prior. So you've got shrinkage towards that sort of prior, which in that sort of situation can actually improve inference, conditional on the number of groups. So it's not precisely relying on the fact that you're considering and comparing the different numbers of possible numbers of groups means that you're less vulnerable to, basically overfitting.
Okay, we have another question by Melania Lembo. Hello, you can.
Yes, hello, sorry, it's me. I have a question about basically focusing a question that follows up on
Melania, probably not Melania.
Definitely. Yeah. So Niall was asking a question about some work that he has been doing in some of the kind of dynamic approaches to kind of latent space clustering, and one of the ones was the ones that he introduced, but clearly even some of the examples that you described, like the monks example, indeed have a kind of a temporal component to all of these aspects as well. So how do you think actually that some of these kind of temporal approaches may become more relevant when it comes to kind of clustering, and does it introduce additional complications, or does it maybe actually result into even some ways of making things easier? Because by looking at a temporal component, you might actually be able to figuring out prior and what follows afterwards, which may actually simplify things.
I'll have a quick shot at that. I mean, the issue with temporal data is you both have to represent the cross-sectional structure of the network, but also the temporal dynamics of the network. And putting those two together makes it incredibly flexible. The amount of data we have, even for temporal measurements, is relatively modest. So I think one of the concerns in this area is that the inference tends to lead to very uncertain outcomes. And in particular, simple visualizations, which are very reductive, sometimes lose the overall uncertainty of the situation. So I agree that these temporal models are very important and from a scientific standpoint, very worthwhile working on. We have to be very careful with them, though, just due to the relative lack of information we have about the processes involved.
Yeah, I'd just add one quick thing, which is I think that there's a certain sense in which inherently the whole process is temporal, because the reason you've got clustering in networks is that clustering evolves over time, right? People meet one another, they meet other people, they get together as groups, they form friendship groups and so on, and that's an inherently dynamic process. So when a lot of the data is a snapshot, and that's we're approximating a dynamic process by a snapshot. So so to some extent we can't actually get looking at the snapshot alone, we can't replicate or get at the underlying process. The problem is, of course, we don't observe things with enough temporal resolution to actually see that going on often. So we do the best we can, and the clustering model is a kind of it's an approximation of the results of these temporal processes rather than something that's inherently present.
Okay, is there anybody who would like to add something? Kind of the RSS organizers kind of expressed to me that they put a lot of confidence in me ending this more or less in time, which doesn't always work. So kind of, despite the fact how nice this all is, I think probably then we reached the end. I gotta tell you that full details of all upcoming journal webinars are available on the RSS website and announced in members' newsletters and on X Twitter. If you would like to receive an invitation to future journal webinars, email journal@rss.org.uk and we'll add you to our mailing list. And I'm very happy how this has turned out, and I thank, of course, the presenters, the discussants, and all of the audience, particularly also the audience who contributed to the discussion. And I wish you all a pleasant evening. To some people, it may be a different time of day, but I haven't figured that out. So you can have a pleasant evening when it comes. Okay. Bis dann.
Thank you.
Okay. Thank you.
Thank you so much.
Everybody.
Bye.